So we'll start with 1 minute early, because we are very serious. Okay, so it's a pleasure to welcome Claire Boyer from Paris 6, and Claire will speak about compressed sensing and realistic sampling schemes.
Okay, thank you for the invitation. I'm very pleased to be here. So the talk is about a realistic sampling in compressed sensing. So if you're passionate by compressed sensing, then this talk is for you. But if you get bored to compressed sensing, this talk is also for you, because there is another part where there is no compressed sensing anymore. Okay? Okay, so I will first introduce the problem that we are looking to, and we are going to derive theoretical results, and then we are going to try to design in practice efficient sampling strategies, and mainly in MRI. Okay, so the starting point of this work was given by Philippe Siussiu in the CEA in Saclay, in Neurospin. So this is a neuroimaging center where they have MRI coils, and it's like the best European neuroimaging center, let's say it. And so we've been working on the problem submitted by Philippe with Jérémy Bigot and Pierre, mainly for the first part, the theoretical part, and with Pierre, Jonas, and Nicolas on the second part, meaning for deriving sampling strategies. Okay? Okay, so I'm going to focus on MRI. If you follow the course of Anders, you already know a bit about it. But just keep in mind that what I'm going to say can be also applied in other application fields. So yeah, we just keep MRI as a red thread, and then you can try to apply it to any application field that you want. Okay, so in MRI, if you remind what Anders says, you got an image, you here, that you want to reconstruct, but you observe only the Fourier transform of this image, okay? And actually, you don't want to observe it fully because, well, it's long and blah, blah, blah. Okay, so you are allowed only to sample stuff along smooth trajectories. So if you parameterize your trajectory by lambda, you have some constraints given by the electromagnetic principle of MRI, and then you should satisfy those two conditions, meaning that you have speed boundedness and also acceleration boundedness. So you cannot go too fast in an MRI, and you cannot turn too much while going too fast in an MRI, okay? So typically, you can consider here a spiral, right? A spiral will satisfy both constraints. Okay, but on the spiral, you won't take an infinite number of measurements. You will just have a subsample, okay? So a subsample of measurements along this trajectory here. Okay, so the question is now, if you sample at rate delta t on your spiral, you have access to a set of measurements that you can call E lambda, and E lambda is just the Fourier coefficient of the image U, so U hat, view at the frequency lambda k delta t, okay? And then the question is, from E lambda, your set of measurements, can you reconstruct U, your image? How do you choose your set of measurements in practice? And how you will generate a curve, a sampling curve in your MRI machine? Okay, and for all this stuff, of course, you want to have the minimal number of measurements as possible, because you want to speed the acquisition, okay, and save time. Okay. So again, what I'm saying is only for MRI, but you can apply it for tomography, ultrasound imaging, interferometry, or even mobile sensing, okay? But you just have to adapt the theorem to this context. Okay, so of course you all know about sparsity now. So let's say that we have a support of my signal. So my support is big S, my signal is X, and X is sparse if it has at most S non-zero coefficient, and of course S will be less than N, the ambient dimension of the space where my signal is living. Okay, and in practice, you already know that most natural images and even brain images are actually compressible in the wavelet domain, saying that here, if you just throw away 99% of the coefficient in the wavelet domain of this image, you end with this one, and then you have preserved all the information. So typically when you want to reconstruct a brain image, you're going to say that this is sparse in the wavelet domain. And then if the sparsity is in the wavelet domain, you are going to want to reconstruct the wavelet coefficient and not the image, okay? So you just want to reconstruct the wavelet coefficient of the image because this is this which is sparse. Okay, so more formally, you can call psi to be your orthogonal transform, your orthogonal wavelet transform, and then your signal U, your brain image, can be written in the wavelet basis, psi x, and then x are the wavelet coefficient that you want to reconstruct. And by the electromagnetic principle of MRI, you're going to want to sample in the Fourier domain. So, in fact, what you are doing, you're modeling your acquisition in the MRI case with A0, which is your full sampling matrix, your full sampling operator, which is just the Fourier transform and the inverse wavelet transform, okay? So you observe the Fourier transform of the image, but you're going to reconstruct the wavelet coefficient, so you can model your acquisition of your wavelet coefficient at the Fourier transform times the inverse wavelet transform, okay? So of course, A0 is the full sampling operator, so meaning that if you have a signal of length n, A0 can be a matrix of size n by n, okay? And you're going to subsample in the acquisition space, so it means that you're going to subsample rows on A0, okay? So finally, you don't take every rows of A0, you just take a subsample of it, and then you're looking on YK, which is your kth observation, and this is just the scalar product between AK, so some random row selected in A0, against X, the Fourier, the wavelet coefficient of your image. So finally, you can model your subsampling step with Y to be equal to AX, where A is a rectangular fat matrix, okay? Okay, so you already know that in compress sensing, we are promoting sparsity using an L1 minimization problem, okay? And we are interested on guarantee, theoretical guarantee, on the required number of measurements, meaning the number of rows here in A, or the length of Y, if you prefer, to have exact recovery or stable and robust recovery of our signal. Okay, so to derive theoretical result, we are facing combinatorial issues, and if you want to avoid combinatorics, you can use randomness. And actually, most of theoretical results in compress sensing heavily rely on randomness of the sampling matrix, okay? So meaning that if you have something random, you're going to have a recovery with high probability. And yeah, so this is the goal. You want to have a minimal number of measurements M in your sampling matrix A here, but A is going to be considered as random. So you want to ensure the reconstruction of X, the signal, using L1 minimization problem with high probability. Okay, so you already know a bit about compress sensing, right? But let me just do a brief history of it. So if you look at the seminal paper in compress sensing, the one from Candace, Tao, and also Romberg, they are considering uniform drawings. So meaning that if you are in the acquisition space, here, this is the 2D acquisition space, you're going to randomly take samples in this space, okay? And uniformly. So if you do so, you can define the coherence that you already know, right? Because Anders already introduced it to you. And the coherence will be defined like this. So n, the dimension, times the maximum of the squared of the L infinite norm of the row of each row of my full sampling matrix A0. So Fourier times wavelet in the case of MRI. Okay, so you may know that this actually is catching the ability of A0 to spread out the information. Why? Because don't forget that A0 is an orthogonal transform. Okay, so you know that the rows of A0 have L2 norm equal to 1. Okay, and then if you require that this is small, it means that any coefficient in a row of A0 will be turned on, will be non-zero. Okay, so it means that if you have something really sparse in the input of your matrix, of your sampling matrix, since here AK is spread out over all the components, you're going to make an average, okay, a linear combination of the spikes in your input signal. So if you have something very localized in your input signal, you're going to have always information in the output, and this you will have it actually anywhere where you are going to sample in the 2D space. Okay? Okay, so if you consider here, you draw M samples uniformly at random in the 2D acquisition space, and then you can show that if M, the number of measurements, is bigger than the coherence times the logarithmic factor, the degree of sparsity S and logarithmic factor, then you will have exact recovery with high probability. Okay, so of course you can try to do so in an MRI, and of course it won't work. Tutorial is just an exclamation mark. Okay. Okay, so uniform sampling, we forget about it. Then they introduced the notion of variable density sampling, so meaning that now in your 2D acquisition space, you're going to sample more atoms that are coherent, meaning atoms that have a lot. You're going to end up with such a sampling scheme here. So you're going to sample more in the low frequency and less toward the high frequency. Okay? Okay, so in this case, you're just choosing the kth measurements with probability pi k, or no, sorry, PL here, or P coherence. You're going to have a number of measurements with of the order of the coherence times the degree of sparsity. And this is actually better because now this coherence is equal to log n. Again, this is an exclamation mark. But still here, okay, you can say log n is a lot, even if people mainly say it's not. And again, you cannot do acquisition like this in an MRI because it's based on isolated measurements. Okay, it's not rely on smooth trajectory. Okay, and then the late work of Anders, Hansen, and Ben Adcock managed to kill a log factor, and here, so they managed to kill here the log that appear from here, okay? And how did they manage to do so? By considering a special class of signal which has a special sparsity structure, okay? But again, they end with a variable density sampling here. But now they don't have result for any signals, just for sparsity by level signals. Okay, but the problem of this is measurements, and in practice you cannot implement it on the MRI machine. Okay, and then when you look at paper in compressed sensing, they are selling compressed sensing, saying that you can apply it in MRI, and of course we got all the previous theorems that I show you, and then they put this in the numerical section, and then that's it. But actually there is no compressed sensing theory that can explain why, if you sample like this, you're going to have good reconstruction result, okay? Because here there is actually no randomness, but this is totally heuristic, okay? Okay, and in practice, okay, so if I just wrap up what I've just said, here you have a typical compressed sensing sampling scheme where we do IID sampling according to some variable density distribution, okay? Given priority to low frequency, and we have good reconstruction result, and we can also reconstruct a little sentence that I've inserted here. But actually, if you structure the acquisition and you take like horizontal line in the Fourier space, you can still reconstruct your brain and quite accurately. Okay. Okay, so the purpose of today is to try to justify why you can structure the acquisition and still have good reconstruction result. So in this talk, I will only consider L1 minimization problem because I'm from the school of Anderson, actually, where we better choose the measurements instead of fighting once you have the measurements with the post-processing procedure, okay? So I prefer to have the right information in the beginning of my recovery algorithm instead of fighting with recovery algorithm behind. Okay, so the first part, we are going to have compressed sensing compatible with the structure acquisition. That's what you have in practice. And on the second part, we are going to see how we can, in practice, design a structure sampling scheme. Okay? So this is compressed sensing, and actually this is not. Okay, so part one. So the idea is that since we are not clever enough with combinatorics, we have to use still randomness, right? So if we want structure and randomness, the idea is to introduce the notion of blocks of measurements. So a block of measurements is just that if you consider A0 here to be your full orthogonal sampling matrix that model your acquisition, again, MRI Fourier times inverse wavelet transform, you're going to partition A0 into blocks of measurements, and blocks will be just rectangular submatrix of A0, okay? Okay, so you have A0 here, you partition into blocks BK, you have a number big M of blocks BK, and then you're going to draw randomly blocks, BK, and you just concatenate. And now, beware, because the number M here is not the number of measurements that you do, but this is the number of blocks of measurement that you take, okay? So if you want to count in terms of number of measurements, actually you have the number of blocks times the size of the block, okay? So let's take an example. So first, we have this, which is deterministic. You can do it. You can choose the blocks that you want in your transform, in your A0, okay, here. But then you're going to sample randomly in this dictionary of blocks according to some probability distribution pi. So let's say that you choose the kth block with probability pi k, okay. And you should also satisfy this, this condition, which is the isotropic condition, where the expectation of B star B is equal to the identity. So what does it mean? It means that at least in expectation, you're going to be an isometry. Okay? And then you're going to preserve all the information that you got in the input signal. So in practice, you can say that a block in your blocks dictionary can correspond to this horizontal line here in blue, and then you pick the corresponding block, okay? And then you want to sample the orange line, and the orange line is just corresponding to another block in your dictionary. This is B2, and you concatenate it, and so on, okay? And so you end with a concatenation of random blocks here, where B1, B2, B3 are just ID copies of B, which is under the law of pi, okay? Okay, so typically, when you look at this kind of sampling strategy, this is the case. You're just choosing randomly horizontal lines, okay, according to some probability distribution, which is higher in the center, okay? And if you do so in practice, you have good reconstruction results. Okay, but theoretically, is it a good way to start? Is it a good context? Actually, no. Because if you consider that A0 here is a d-dimensional separable transform, let's say 2D, okay, for our case in MRI, and separable transform it is because we got the Fourier and we got the wavelet that we can see has separable transform. So meaning that you are just tensorized 1D transform. So if you do so and you do acquisition like this here, or horizontal lines in the 2D acquisition space, you can show that if the number of horizontal lines that you take is less than 2s the degree of sparsity, then there is no hope that you can decode any sparse vector. Okay? So this is a bad news because here you ask, so a necessary condition to be able to have uniform recovery is to have m, the number of blocks of measurements, so of horizontal lines, to be bigger than 2s. So you're asking to have 2s times the size of the block. So in the 2D case, you ask to have 2s times square root of n measurements, which is huge. Okay? And in practice, here, you don't have it. We don't have this limitation. So when in this paper of Lustig and Dono and Pauli, they sell compressed sensing by drawing lines here in a 3D case. Actually, you can show that if you structure the acquisition like this, then you will be incompatible with uniform exact reconstruction. Okay? You can construct a counterexample that you will never manage to reconstruct with such a sampling pattern. Okay, so the key to break these limitations is just to say that instead of doing like all standard compressed sensing results where they ensure the reconstruction of any sparse signal, we are going to reconstruct not any sparse signal, but some specific one, because in practice, signals are very structured and more structured than just sparsity. Okay, so we need, from this preliminary result, we need a compressed sensing theory or framework that encompass on the one hand structured acquisition, on the other hand structured sparsity. Okay. Okay, so let me do some heavy definitions first. So n is the dimension of the signal that we want to reconstruct, and the signal is supported on S. Okay. M is the number of blocks of measurement that I need, and I will just write BS to be the block B, where I restrict the column that are indexed by S. So it's just that you are looking to the columns of B, of your block matrix B, that interact with your signal, okay? And BK, the block dictionary. So we can define a new coherence, let's say, and we will call it gamma S pi. And gamma S pi, so S is the support of your signal, and pi is the way that you draw your block B. And gamma S pi can be written at the maximum between upsilon and theta. Okay. Theta is here, upsilon is here. Upsilon is nasty. We managed to kill it actually 2 or 3 weeks ago with Ben Adcock, but the paper is not written, so let's keep it on this slide. Okay, so, but we are going only to focus on theta. Okay. So theta is defined like this, you look at the infinity to infinity norm of bk star, bks, restricted to the support, and you renormalize by the probability of drawing the kth block. So actually, in all the in all the examples that I will show you, those two quantities match, always match, in application that I've considered. So that's why we wanted to kill one, okay? And the second point that I want to say is that d theta is exactly corresponding to the standard coherence times the degree of sparsity when you are doing not blocks of measurements, but just raw measurements, like standard isolated measurements, and that you only have the assumption on your signal that this is sparse. Okay, so a few comments. The first one is that it's totally different from RIP, right? Because here I'm depending on S, the support of the signal, so I'm not uniform in every sparse signal. And quantities, of course, are dependent through pi here, and support dependent through S. Okay. And here is the meta theorem, let's say. So if you have the support of your signal X to be S, if you ask the number of blocks of measurements here to be bigger than gamma S pi times logarithmic factor, then you can show that you will reconstruct exactly your signal with high probability. Okay, so there is a log S factor, but it can be discarded here. And luckily, Guillaume Lecuyer is not here because he cares a lot about log factors. And, and the proof is actually based on the golfing scheme that has been introduced by David Gross in the case of low-rank matrix recovery. And actually, I want to say a few words about it because it can be of interest for you, I guess. But I won't go into the proof into details. Okay, so the first thing to say is that you want to ensure that basis pursuit, so this problem, L1 minimization that you have here, adequation to your data. Yeah, so, well, maybe I don't have time actually. Okay, well, we want to solve this problem and to show that you have a unique minimizer, which is X. In RIP-like method, RIP-like method, you're asking that the probability to reconstruct using basis pursuit any sparse vector is bounded below by 1 minus eta, where eta is small. And when you do non-uniform recovery, you're not asking this, you're asking that for any fixed X, okay, with support S that you don't know, of course, but this is fixed, you're going to bound below the probability that basis pursuit will uniquely recovers your signal. Okay, so this is the difference between uniform strategy and non-uniform strategy in compressed sensing. Okay, so if you do non-uniform strategy, you're going to want to construct what we call a dual certificate. And a dual certificate comes from where? Comes from Fermat's rule here. Okay. So you know that X will be a solution to your basis pursuit problem if there exists some H here, such that 0 is in the subdifferential, the normal cone of your constraint set here, okay? And you can write it as A star H, okay? So this is just, again, generalizing the fact that if you're differentiable, you ask the gradient to be 0, and when you are not, you're just asking 0 to be in the subdifferential. Okay. So we need to find an H such that A star H on the support is equal to the sign of XS, because this is the subdifferential of the L1 norm, and outside of the support, it should be less in magnitude than 1. And actually, you can say that if A, your sampling matrix, is injective on the set S of vectors supported by S, and if you constrain A star H to be strictly less than 1 outside of the support, then you will have uniqueness of the solution. So again, Carlos Fernandez Granda talked to you about this in the case of super resolution. So this is the same problem. And people are calling V, which is equal to A star H. So all the thing in the proof is to be able to construct such a dual certificate. Okay. Okay, so maybe I won't, I will skip this part. So the thing is, you're going to want to construct a dual certificate. There is one which is really nice. This is this one with the L2, the minimum L2 norm, okay? And actually, Candace managed to construct such a dual certificate with high probability using combinatorics. But there is another way to do it, is that you relax the constraint that you are exactly equal to the sign of x on the support, and then you restrict here to be outside the support to be far from 1. So if you just manage to construct an inexact dual certificate like this, then it's enough to show that you have exact recovery and uniqueness of the solution. And so the idea of David Gross was to design a golfing scheme, and the golfing scheme is just an iterative process that allows you to construct such a dual certificate V. Okay? Okay, so, but I will skip this. Okay, and then, so we just do the golfing scheme, and we adapt it to the block case, of course, because we are in the block case. So just a few words. We can also handle noise in the observation, meaning that we are not interested now in the basis portrait, but in the basis portrait with quadratically constrained here. So meaning that you want to minimize the L1 norm such that the distance between your data and AZ is bounded by eta, and typically eta is just the level of noise, meaning the 2 norm of your noise in your observation. So we got a stability result, but has any non-uniform result, because here we are considering a fixed signal x, we have this kind of bound on the recovery. And actually, this is an open question to know if we can improve this bound by removing the square root s here and dividing here by square root of s. So please, if you have idea, I got obsessed by this question, and so you should let me know. Okay. So now we have a meta theorem. We can try to apply it in practice, right? So let's see what it gives in the case of isolated measurements, which is the standard setting in compressed sensing, where you just pick isolated measurements, meaning that you just take random rows in your matrix, and then your blocks are just rows, okay? Okay, so if you do so, and A0 is just any orthogonal transform, you got the prior on the support S just to be S sparse, like in standard compressed sensing, then you end with the number of measurements, which is S times the standard coherence. Okay, so we match the standard compressed sensing setting. Okay, now let's turn to a silly case, which is the case where you consider that your sample with the identity, which is a really bad idea, because if you randomly sample the identity, there is a high chance that you miss all the information, right? Okay, but the thing is now, with the previous theorem that I show you, you can inject some prior on your support, okay? And let's say that you have a heavy prior on the support. Let's say that you know your support, okay? So if you know your support, then you can uniformly sample on the support, which is natural, right? And then you will end with the number of measurements to be equal to S times logarithmic factor, which you can associate to the coupon collector effect, if you know it. And okay, this is a toy example, but it's just to say that if you have coherence in your sampling, you're not doomed as soon as you have enough information on your support, and you can inject it actually in the theorem. And then you would end with this number of measurements. Because if you use those two information, the identity with the support in standard compressed sensing result, you still end with the number of measurements here to be bigger than n. Okay? So there is no way to inject information on your support. So actually, the theorem allows you to do it. Okay. And the last case where we do MRI and we consider the support to be sparse by level, then we find the same result as Ben Adcock and Andersen and Claris and Bogdan Roman. So this is perfect. We match the state-of-the-art result. Okay? But we are not interested in isolated measurements. We want to do structure measurements, right? So let's do structure measurements. So on this slide, I will only focus on the case where I'm acquiring horizontal lines in a 2D setting. Okay? So I'm in dimension n. I have a 2D acquisition space of size square root of n, and I just take horizontal lines at random. Okay? Okay, and m here is just the number of lines that you take here. Okay, so you recall that in the first limitation proposition that I give in the introduction, I said that if A0 is Fourier, so it's separable, and if I only know that my support is S-sparse, I have a necessary number of measurements that should be bigger than 2S, okay, which is really bad. But with the new theorem, let's say that you have still Fourier, but now you have some prior on the support that say that you're concentrated on Q lines, Q horizontal lines, in the space domain, not in the acquisition space. Okay? So if your sparsity is structured along Q lines, then you can show that the number of horizontal lines that you need is of the order of Q, the number of non-zero lines in your signal, and not the number of non-zero coefficients. Okay, so let's take this example. So here I have a standard sparse signal, which is uniformly sparse. Okay, I look at it through the Fourier domain using this sampling scheme structured along horizontal line, and this is the reconstruction, which is bad. I don't have exact reconstruction because here I have some artifacts, right? Okay, now I consider another signal here, which has the same amount of sparsity than before, but now the sparsity is structured along horizontal lines. And I still observe it through the Fourier domain using the same sampling scheme as before, and now I reconstruct perfectly this. Okay, so the previous result was just saying that indeed you can do something with this sampling scheme if the sparsity is structured accordingly to the structure that I have in the acquisition. Okay, this is quite natural, but again, it was just to have a formal result explaining so. Okay, and again, you can say if I'm in the case of MRI, so A0 is just Fourier and the R wavelet because we have to do some computation, and you are happy when you have R wavelet. The question is, what should be the prior on the support when you acquire horizontal lines like this in the Fourier space while you want to reconstruct Fourier wavelet coefficients? Okay, so what it is, I will try to give you insight. It's a bit technical, but well, it's okay. Your first guess could be the answer of Anders on Monday, saying that you should consider the sparsity by sub n. Okay, well, the sparsity by 7 SLL prime. So this is the 2D wavelet domain here. I have my 2D subbands, and Anders needed information about the number of non-zero coefficient in each rectangular, right? Okay, let's go back. Okay, so actually this is the structure that you need here when you are doing isolated measurements. But when you structure the acquisition, this is not the structure, the sparsity structure that you need anymore. The sparsity structure that you need is this one, is the number of wavelet coefficients that are non-zero, but that are maximally aligned along horizontal, vertical columns here, okay? So let's say that for each horizontal level, you're going to count where you have a maximal number of non-zero wavelet coefficients here that are aligned along a column. And then this number will give you S0C in these levels. Okay? S0C and C is for the column. And then you're going into the second horizontal levels, and then you got S1C and so on. Okay, so if you got such information on your signal, then you can show that the number of horizontal lines that you need in Fourier should be bigger than this quantity of interest, SGC, so the structure sparsity, the weird structure sparsity in your signal. So again, just to fix the idea, it means that if you have a signal that reach here, this kind of structure sparsity as before, it means that in the Fourier domain, you're going to take a proportional number of horizontal lines proportional to this number of black dots that you have in each horizontal levels. Okay? So let me show you a numerical experiment where we are considering this bamboo image. And let's say that this bamboo image, we are observing it in an MRI machine. Okay? So this is parsed in the wavelet domain, and we observe it in the Fourier domain. So if you do so, you have this image V, and you can rotate it as the image H. Okay? So this is the same image, but just rotated. And actually, if you acquire a sample in an MRI, which is natural, is to say that, okay, I should need as many samples for this one than for this one. But this is not the case when you structure the acquisition. Why? You can try to evaluate the weird structure sparsity that I just introduced to you before. You evaluate for this image and for this image, and you see that for V it's okay, and for H it blows up. Okay? Okay, so remember, V okay, H blows up. And you use the same sampling scheme for both, okay? Based on horizontal lines. V okay, H blows up. This is the reconstruction of V, okay? H is not good, okay? So this was actually predicted by the previous result because the structure in H is not appropriate for my structure in my sampling scheme, okay? Okay, so this kind of result, the compressing result with structure acquisition and structure sparsity allows you to use more coherent transform if you have enough information on your signal. And of course, there are tough questions remaining, meaning that how can we extend this theory to any arbitrary physical constraints? And actually, if I give you a deterministic sampling pattern, what kind of signal can you reconstruct? This is a tough question remaining in compressed sensing. Okay? There are also other applications that I didn't mention, but this is parallel MRI, and this has been done by Ben Adcock and his postdoc. Okay. So now I'm happy because I'm happy because I have theoretically justified why I can structure the acquisition. Okay, this is good. But I need to give a sampling scheme to the practitioner. Okay, because he doesn't care about my theorem. Okay, so one way to do it is to say I have a blocks dictionary. I know that I should draw from pi. What I could do is just to minimize the bound on the number of measurements that I got in my theorem, and I just try to minimize it with respect to pi here. If you do so, actually you're manipulating huge objects, which are matrices. So in the previous case, it was okay because I do all the computation analytically, but in practice, it's going to be hard to do such calculation analytically. So you want to do it numerically, and then you have huge objects, so you cannot do it. And actually, if you want to minimize with respect to pi gamma, you're going to minimize the maximum between this and this with respect to gamma. This is non-convex. I don't want to do so. Okay. So this part is only using numerical strategies, but quite interesting ones. Okay, the first naive approach that I attempt with Pierre was to be given target density P, okay? So you can think about it as the radial density given by compressed sensing theory, okay? You know that if you are in compressed sensing, you should sample, in the case of MRI, according to some probability distribution, which is radial, okay? But you cannot do it in practice. You cannot sample IID samples, isolated measurements in an MRI machine. So what you can say is, okay, I can define a dictionary of admissible shapes, like horizontal lines, and said that I should set pi, the probability, the drawing probability on my dictionary to look like P. And then I will just do IID drawings according to pi of my admissible shapes. So what does it mean? It means that if you have this target density P here defined over all the domains, you get a blocks dictionary which is just line here, and you're asking how should I set the drawing probability on pi to be able to draw lines. And when I draw IID lines in this dictionary, I should look like sampling IID here. Okay? But this is suboptimal, right? Because you're doing IID sampling. So it's not really good. But if you like optimization, you should look in this paper. There are, and if you like Nesterov too. Okay. So let's forget about this first naive approach, and we're going to do something more efficient. So the more efficient thing is that if you want to have a good sampler, a good sampling strategy, it should have a good empirical measure, okay? So meaning that you should fit some target density, again, the radial one for the MRI, right? And also it should have a good mixing time, meaning that you should be able to cover the space rapidly, which you're not doing if you do IID sample, right? Because with IID, you will have some cluster. Okay. So we should have a prescribed density that we have from compressed sensing theory, good mixing properties, meaning that I should cover the space as fast as possible, and that I should also satisfy some constraints given by my acquisition device. Okay? Okay, and then the strategy that we use is actually inspired by half-toning. So I will first introduce half-toning, and then I will present you how to use it in the case of MRI. So half-toning is something happening in your printer, okay? When you want to print a grayscale image, you can see it as a continuous thing, and your printer is not going to print something continuous, he's going just to do black dots, okay? And he's going to put more black dots where you have black regions in your image and less black dots when you have white regions, okay? So typically, if you got this image here to print and you have a very bad printer, you're going to end with this line here, okay? And actually, you have just here set points or Dirac masses, let's say, but points, black dots, in order to look like this image, okay? And normally you're able to say that, well, this lion is this lion, right? Right? Right, okay. So why are you able to say that this is the good half-tone version of your lion? Do you know it? There is no math here, so feel free to answer. Okay, the first reflex could be to compute the L2 difference, right? But if you do so, well, you will have a huge discrepancy between your target image here and your Dirac masses image, right? So the key is actually to blur these two images. So you blur them first and second and a third time. And then you see that now you cannot distinguish them, okay? So it means that actually your brain is able to see the image at different resolution level, okay? And then even if I give you only those two images, you know that at some low resolution, you cannot distinguish them. That's why this one corresponds to this one, okay? So we are going to use this idea. We know that we should sample, so this will be my target density here, but in MRI it will be radial. It's not a lion. So we should sample ID sample from this, but the question is, if I have a fixed budget of points here, this is my only constraint, I just want points, how should I place them in the space so I look like my lion, okay? So the key thing is now we have a fixed budget. We don't do ID sampling, okay? Okay. So half-toning can be reformulated as a measure projection problem. So you have the constraint set M to be mu, and mu is just a sum of Dirac masses uniformly where you put a uniform weight on it. And you ask to minimize some distance between mu, your Dirac masses measure, and P, your target density, your lion, or your radial density in the case of MRI. Okay, and for DH, you're going to use this distance, the square L2 distance between a blurry version of mu and a blurry version of P. Okay? And actually, this problem here can be, you can expand the L2 norm, and then you will end with the problem where you have here a repulsion minus an attraction potential. Okay? So this potential is going to ensure that the weight in your Dirac masses, the location of your Dirac masses are where P, your target density, has high density, so you will look like P. And here, oh, sorry, there is a typo. That should be a W here. So Wi minus Wj. Here, this repulsion potential will ensure that you don't have two Dirac masses too close, because you should cover the space. Okay, so you should repulse the Dirac masses location. Okay. Okay, so actually half-toning has been studied by this a lot of people, and this German school has provided some numerical tools based on non-uniform Fourier fast transform to do fast summation method, and you can do it with the parallel implementation. And actually, you just do a gradient descent, and it works well in practice. Okay, so this is a non-convex problem because you have a difference of two convex function, the repulsion potential and the attraction potential. We just do a gradient descent, and of course you don't know if you converge to a minima. You just converge to a critical point, but the critical point is quite good. Okay. Okay. So now the idea is just to extend this idea of half-toning to the case of MRI, because I don't want just Dirac masses. I should be along smooth trajectory, right? So my constraint now will be measure supported on curves, and so my curves are just the one of my MRI machine, so I should have bounded speed and bounded acceleration. Okay, so again, alpha and beta are given by the MRI machine, and we are going to define m lambda t to be measure through the parametrization lambda. So this is big words to say what? To say that if you have here this admissible curve that you can implement on an MRI machine, you parameterize it by lambda, and then you're going to say that the measure mu b of the Borelian b is just the time that you spend in the Borelian along the curve divided by the total time that you need to go through the whole curve. Okay, so this is just this length divided by the total length. Okay, and then your measure projection problem can be written like this. Okay, you minimize the distance between mu and p, p your target density, and mu is living in this constraint set. So measure supported on curves. Okay. Again, you can discretize your problem. You can rewrite it as a repulsion attraction potential, and you can do a projected gradient descent using quite a while. But actually, we don't care, because once you have compute the sampling strategy, you have it, and you can implement it on an MRI. Okay, so you just need to compute it once. Okay, so if you take this kind of target density for the MRI, right, the radial stuff, you can try to project it on the space of measure supported on curves or supported on horizontal lines or segments of variable lengths, whatever you want. And this is actually the output of our strategy, here for straight segments, okay, and here for curves with bounded speed and bounded acceleration. And actually here, this is just a zoom in the center of the image, okay, just you to be able to see that, yeah, this is straight lines and this is something curvy, okay. So when I show this kind of sampling strategy to people, applied or theoretical, they are quite skeptical to say, yeah, you cannot do it in MRI. And so actually in simulation it works pretty well, and it outperforms heuristic strategy based on radial lines. And we managed to reach really high resolution, which is still unrealistic for MRI. But as Anders say, you can use compressed sensing just to enhance resolution if it's not for accelerating the acquisition, right? Okay, so in simulation it was quite good, and then there is actually, so this is just a zoom for another sampling scheme, but there is the PhD student Carol Lazarus in Neurospin who is implementing this on real MRI scanner. This is actually a PhD thesis, just to implement this kind of thing on a scanner, because you have to code electromagnetic gradients, so this is quite hard. And everything is confidential, but I can say to you that it's going to be awesome, okay? Okay, so there is also a way to use what you do for MRI people and to do more fancy stuff. And the more fancy stuff is this one. So let's say that you're not gifted in life, not like this person. So this person is doing a commercial for Faber-Castell. And so he's using Faber-Castell pen, of course, and he's just drawing on a sheet of paper, and he's just turning around. And after many minutes or many hours, I don't know, he ends by having this painting, La jeune fille à la perle. Well, I don't know the English name, sorry. Okay, so this guy is gifted, I'm not. So what I can do is just I can use my computer to do such a thing, right? And I can say, okay, now my constraint is this kind of thing, okay? It's just a curve that's going around. And actually, I didn't take this. I just say, okay, I just want a continuous curve to mimic some image. And this is how you end having a good birthday gift for your friend when she's turning 30, okay? So this is the 2D version, and there is also the video version. Let's say this is not a 3D version, but you can take on YouTube this dancer, which is doing an entrelacé, and then you can try to project it on the space of measure supported by Dirac masses. And so if you do it with Dirac masses, well, okay, you will have this. Can you see it? Yeah. You will have this. So of course you can see maybe that the algorithm has not converged totally because you have a bit of points outside of the body of the dancer, but well, it's just an art effect. Okay, and then you can project on the space of measure, and now when the algorithm has not converged, well, you have this kind of voile, I don't know how to say it, okay? And if you like abstract art, you can just project it on segments. Okay. Yeah. And the thing is, if you are jealous of stars, you can also do it with the Beyoncé video clip, right? You can just take Beyoncé. She has already great curves on her body, so you can project it on straight lines, of course. Okay? And actually, I didn't realize that it was recorded, so maybe I don't have the right to diffuse Beyoncé. But I hope that Queen Bee will be tolerant. Okay, this is for science glory. Okay, so I should stop there, and I should thank you for your attention. So if you have any question, please.
Okay, so questions for Claire?
So I think this is quite impressive. Like Anders told us, like on Monday, I think, that actually there's an option to get like a random sampling in a plane if you take a 3D acquisition and you just take a slice. And then you can apply all the compass sensing theory as it has been there. And do you have any intuition of how that compares in the end? Because on a scanner, it should be easy to shoot those lines in 3D. And this, I guess, is a little tedious, as you said, to implement it. Like if you want to do like some random stuff in 2D. Do you have any intuition of time that you need in the end to do those scans, or is that?
Okay, so in the simulation, we really take the same time that you need to go through the curve, that the time that you need to do radial sampling schemes that are used in practice. So in the simulation, we have the same amount of time, okay? And we have the same subsampling rate. Well, you can do both. Either you do subsampling rate, but this is not what is important. Which matters, is the time that you spend to sample, okay? So in this simulation, it works. And in practice, so this is only the works of Carol Lazarus, which is not out, right? But it works also. So this is a big problem because you have in practice many problems like inhomogeneity in your signal. But okay, in practice you can do it. You can do it in 2D, and actually now she's trying to do it in 3D. And of course in 3D I bet it, but well, yeah, I'm pretty sure that it will be more efficient than just taking random lines in the third dimension, because you're just having a fixed budget and you spend it optimally to look like a radial, a radial density distribution. So,
yeah, thanks. I'm looking forward to that.
I just have a quick question. Like when you show that bamboo image, like obviously the image structure is kind of relevant for the sampling strategy, but what you implement, like obviously you can't. So
I can't quote.
Like you can't adapt the sampling strategy to the image structure.
Yeah, so, okay, my setting is saying, okay, I have a sampling device that allow me only to take horizontal line. This is fixed, I don't have the choice. And then I'm just saying that if I have to sample the bamboo image, now it matters what is the orientation of this image, because I have structure in the acquisition. And I can capture the ability to reconstruct both images through the weird structure sparsity. That's it. Yeah, but of course this is a particular image. It was just to illustrate it.
If I understood well the final section, you to compare the dotted the dot projection and the original image, you use an extra measure to blur the differences. But I assume that if you blur too much, I mean, everything looks the same in the end. Yeah. So do you have like a bound on a threshold on the blurring?
So actually, we are not defining the. We are not working on the initial h that I showed to you, the little h, convolved with the difference of the measure. We are working with the repulsion potential and the attraction potential. And you should use a kind of h that you can compute in practice. So in the end, it ends by considering the L2 distance between the points. Okay? So that's how you will ensure that 2 points are not too close, and that your points in your reconstructed measure will fit your density. But yeah, of course, this is a question. In practice, you just choose something that is computable, and after you have to struggle a lot with the non-uniform Fourier transform, which is a big point in the algorithm where you have many parameters, but well, if you're lucky, you end with something quite good.
But don't you want to use a compactly support kernel so that you avoid comparing every point to every point? And
yeah. So we are living in a bounded domain.
Yeah, but even if you have like billions of points,
yeah,
won't it help to have like a fast way to compute nearest neighbors?
Yeah, maybe. Sure. I guess, but in the Daniel Potts toolbox, you have like many options, and you can.
But I think his question was referring to how you scale the typical scale where you compare to the number of points, and I guess it should. If you take more points, you can use a smaller kernel.
Yeah, sure.
Okay, other questions? No. So let's thank Claire.
Yes.
Sorry. Yeah, nice cluster.
Thank you for your talk. How would this work with temporal data, like in functional MRI? And would you have to change your sampling strategy, or would you be able to use the temporal structure of the data?
So for functional MRI, the thing is you have to do it online, right? You have to design your sampling scheme online, and this kind of stuff you cannot do it because this is quite heavy to compute. So, well, actually, I don't know, but yeah, you could study what is the kind of heuristic sampling strategy that they use in practice with the space and time feature, and then see if you plug it in the projection problem, what you would end with. But yeah, we didn't do it. Yeah.
Okay, let me do a final check. No. Okay. Oh, yeah.
I have a quick question about the proofing techniques that you develop. Can you give us a very brief introduction of the proofing sketch and why it is tricky to refine your bound in constructing dual certificate engulfing scheme?
Engulfing scheme. Okay,
Yeah.
So there is two things. So if you want to talk about the golfing scheme, maybe I can explain it to you later because.
But you mentioned that this is an
No.
open problem, so.
Yeah. So I don't know if I can go back. Okay, so the thing is, when you have IRIP, when you have IRIP condition, you can show that the distance between the true signal and the one that you reconstruct is bounded by a constant. The best S-term approximation in L1 norm divided by square root of S plus another constant and the level of noise. Okay? And when you do non-uniform strategy, you basically have the same thing, but everything is multiplied by square root of S. Okay, and I don't know if it's because we are lazy and with this kind of approach we can only have this kind of result, or if the least assumption that you can add to have this kind of stuff in a non-uniform setting, I don't know if it's just RIP, and if it's just, then there is no point to add it. Okay? Yeah, but I don't have the answer. Yaniv Plan doesn't have the answer. Since he was the one with Candace to introduce golfing scheme in the compressed sensing setting. So yeah.
Thank you.
Okay, so I guess it's time to thank Claire for her talk.